It started as a normal day. The factory was running smoothly. The machines showed no signs of trouble. But deep within an artificial intelligence system, danger was detected. A critical failure was imminent. And this time, the technology saw it coming before anyone else. For decades, factories relied on routine maintenance schedules, fixing machines after breakdowns, or performing unnecessary repairs. Then came AI-powered predictive maintenance, a revolutionary system that monitors equipment health in real time, catching failures before they happen. It's like giving machines a sixth sense. Instead of waiting for equipment to fail or relying on rigid maintenance schedules, artificial intelligence-powered systems analyze real-time data from sensors to detect subtle signs of wear, misalignment, or overheating. The goal? Fix it before it breaks. Here's how it works. Sensors monitor vibration, temperature, pressure, and energy use. Intelligent algorithms analyze this data to spot anomalies or patterns that signal impending failure. Maintenance teams get alerts with predicted timelines, so they can act proactively. Let's take a deeper look, leveraging real-world examples. Rolls-Royce's mid-flight artificial intelligence monitoring is a textbook shift from scheduled upkeep to real-time data-driven health checks. Here's the full picture. Jet engines generate terabytes of sensor data, vibration, temperatures, and pressures, every flight. But traditional monitoring only scratches the surface, leaving early-stage faults undetected. Bandwidth limits mean you can't simply stream every data point to the ground. You need intelligence to pick out the needles in the haystack. Enter Engine Health Management, EHM. Each Trent and Pearl engine is wired with thousands of more sensors than before, and it talks back on command, streaming focused data bursts via satellite links to Rolls-Royce's global operations centers. Ground-based neural network models continuously compare live data against decades of flight histories to spot subtle anomaly patterns, blade fatigue, bearing wear, and compressor stalls, long before they cascade into failures. When the intelligent-powered system flags a developing issue, it sends a tailored recommendation such as inspect HPC Stage 3 blade route directly to airline maintenance teams, slotting work into planned downtime rather than forcing an aircraft on ground, or AOG. The results are impressive. Enhanced fleet-wide visibility. Over 8,000 civil and business jet engines are under real-time surveillance through EHM, giving operators a clear picture of engine health across routes and utilization profiles. Reduced unscheduled maintenance. Airlines report up to a 20% drop in AOG events by catching incipient faults mid-flight and addressing them during routine layovers. Higher engine availability, proactive fixes, translate into more revenue-earning hours in the air. Every avoided emergency inspection or blade swap pays for itself many times over. Lastly, safety and predictability, preventing in-flight shutdowns, isn't just about cost. It's about eliminating rare but catastrophic scenarios, boosting passenger confidence and regulatory goodwill. Taken together, Rolls-Royce's AI-powered EHM has transformed jet engine care into a dynamic, predictive service where the engine itself becomes your first-line engineer. Now let's learn how Siemens tackled the pain points of endless downtime and alarm overload with Sensei predictive maintenance, and the real gains companies are seeing. Factories often ran on rigid, time-based schedules, or firefighting repairs. Manually setting vibration or temperature thresholds across hundreds of machines flooded engineers with false positives, making it nearly impossible to know which alerts really mattered until a breakdown strikes suddenly. Siemens found a better way, introducing Sensei PDM. This intelligent-powered tool ingests data, such as vibration, current, torque, temperature, and more, directly from a plant's existing sensors, then applies machine learning models that learn both machine behavior and each maintenance team's priorities. Instead of generic alarms, it surfaces only high-value warnings at the right moment. A newly added generative AI layer even lets engineers chat with the system to query asset health in plain English, making maintenance insights conversational and instantly actionable. Not only did Siemens create the technology, they implemented the solution on over 10,000 machines, spanning more than 100 equipment types that are now monitored remotely by Sensei's proprietary algorithms. Amazing! And we are not the only ones that think so. The proof is always in the data. Inquiries about Sensei have jumped 275% since 2015 as manufacturers shift from pilot projects to plant-wide deployments. By turning noisy data into crisp, context-aware warnings, Sensei PDM shifts teams from reactive firefighting to crystal ball-like foresight, slashing unplanned downtime and stretching every maintenance dollar further. At GE's Asheville, North Carolina, engine parts plant, operators juggled 4 separate parts rotating through 4 distinct machines, each with its own cycle time. This created immense cognitive load. Who should do what, when, and in which order, especially around breaks and unexpected delays. Legacy systems didn't offer real-time guidance, and custom software took months or longer to develop, leaving productivity gains locked behind slow rollouts. So GE built Predix, a cloud-native platform for industrial internet applications that weaves together design, engineering, manufacturing, supply chain, and service into one digital thread and digital twin. Let's explore. Predix's microservices architecture sits atop Cloud Foundry, offering secure, scalable data ingestion and analytics. On this platform, GE Aviation launched the Standard Work Optimization Tool, SWOT, which is another way of saying an app that ingests live machine data and prescribes exactly which action the operator should take next to maximize throughput. Beyond aviation, Predix powers GE's asset performance management and fleet support solutions, replacing a legacy database from the mid-1980s with a modern cloud-based backend. SWOT went from concept to production in under 3 months. Productivity uplift was noticed within the first month. The app delivered a 12% increase in cell throughput where it was deployed. The same Predix foundation now underpins dozens of industrial apps across GE's businesses, accelerating innovation and ROI without rewriting core infrastructure. The technology continues to evolve. Do not be surprised if the next frontier is self-healing factories. As we discussed, artificial intelligence is already shifting disaster prevention from gut feels and fixed schedules to real-time foresight. But what are the faces we see the shift across in emergency management? Mitigation. The technology optimizes where to deploy sensors and creates susceptibility maps for floods, landslides, or urban heat islands. Preparedness. Machine learning models fuse weather, seismic, or hydrological data to trigger early warnings days or sometimes hours ahead of a crisis. Response. Natural language processing on social media, satellite imagery, and Internet of Things. Feeds deliver live situational awareness to first responders. Lastly, recovery. Computer vision and drones speed damage assessments, guiding resource allocation, and rebuilding plans. Take flood forecasting and maritime search and rescue as real-world wins. Google teamed up with the Bangladesh Water Development Board, recognizing that Bangladesh suffers more riverine flooding than any other nation. Through this collaboration, forecasts feed directly into the board's alert infrastructure, so government warnings now leverage AI-driven flood maps and depth predictions, rather than solely relying on historic gauge thresholds. Not to mention the wide population coverage. As of the latest rollout, Google's Flood Hub, its public map-based portal, is delivering daily forecasts for over 1,800 river sites worldwide. In Bangladesh specifically, the service already covers more than 40 million people, with efforts underway to extend coverage nationwide. This means tens of millions of at-risk residents gain up to 7 days advance notice of rising water levels, even in data-scarce rural basins. Crucially, the system also predicts flood depths, such as water may rise 1 meter above embankments, giving communities actionable details to move livestock, stack grain, or reinforce levees before waters arrive. Aurora, Microsoft's cutting-edge artificial intelligence model designed to predict hurricanes, typhoons, and air quality with unmatched precision. The technology was trained on over 1 million hours of data, weather station readings, satellite imagery, radar inputs. It could detect storm formations days before traditional models. July 2023, conventional forecasts misrouted Typhoon Doksuri until just a day or two before landfall. However, Aurora correctly predicted its path 4 days ahead at 2 to 5 day lead times. It was around 25% more accurate than major operational center. In short, artificial intelligence didn't just catch Doksuri sooner, it empowered residents and officials with sharper, earlier insights, turning what was once chaotic crisis management into a more orderly, data-informed fight for safety. Coast Guards leverage artificial intelligence to merge real-time vessel tracking data with weather forecasts, pinpointing likely distress calls, and sending rescue teams before maydays are even issued. Oh wait, there's more. Researchers at the University of Texas at Austin developed an intelligent large language model trained on 5 years of seismic data. During a 7-month trial in China, the system successfully predicted 14 earthquakes, each within about 200 miles of the actual epicenter, and with nearly spot-on magnitude estimates. Here's how it worked. The technology didn't rely on traditional physics-based simulations. Instead, it analyzed real-time seismic activity for statistical anomalies. Used machine learning to detect subtle precursors, tiny shifts in background tremors invisible to human analysts. Delivered weekly forecasts, flagging likely quake zones and intensities. The results? 14 correct predictions, 1 miss, and 8 false alarms. While not perfect, this level of accuracy is unprecedented, especially considering that no other system has come close to reliably forecasting earthquakes days in advance. This intelligent model could revolutionize disaster preparedness. Early warnings mean more time to evacuate or reinforce infrastructure. Economic losses could be slashed by billions. Lives saved through better planning and response. What's next for the researchers at the University of Texas at Austin? Well, the team is now eyeing trials in California, Japan, Italy, and Turkey, regions with dense seismic networks. They're also exploring hybrid models that combine artificial intelligence with physics-based simulations for even greater accuracy. The economic upside is staggering. Insurers, utilities, and municipalities report that early warning intelligent-powered systems have cut emergency response costs by up to 30%, which is usually covered with taxpayer money, and prevented billions in asset damage. In one region, an AI flood alert network saved over $200 million in avoided crop losses and infrastructure repairs during a single monsoon season. Yet, as AI's power grows, so does the transparency dilemma. Stakeholders fear opaque models making life or death calls without clear reasoning. A recent Harvard Business Review study flags 12 trust risks, from hallucinations to ethical bias, threatening adoption unless addressed head-on. Building confidence means pairing predictive systems with transparent, human-centric controls, such as explainable AI dashboards that show why a flood warning was issued. Human-in-the-loop protocols, so responders can vet or override critical alerts. Standards for data provenance and algorithmic audits to ensure robustness and fairness. Predictive AI's promise hinges on 2 pillars: transparency and partnership. When models don't just spit out warnings, but explain their logic in clear dashboards, operators can see the why behind every alert. Coupling that with human-in-the-loop checkpoints ensures that critical decisions, whether to reroute floodwaters or swap an engine blade, remain grounded in expert judgment. Robust data governance policies, periodic algorithmic audits, and open model cards further cement trust by showing stakeholders exactly how these systems learn and evolve. Looking ahead, predictive artificial intelligence will be a ubiquitous safety net woven through every industry. Smart cities, routing traffic around accidents before they happen. Energy grids, auto-adjusting to prevent blackouts when demand spikes. This is definitely needed in Texas, because I hear great energy grid concerns anytime there is an extreme weather event. But I digress. And maybe, most importantly, healthcare networks, flagging viral outbreaks at patient zero. As the technology reach grows, the goal should also be that our confidence matures in parallel, driven by transparent tools, clear governance, and seamless human-AI teamwork. That way, in the future, predictive intelligence won't just save billions in losses. It will become our most reliable co-pilot against the next big crisis. If you enjoy knowledge on technology predicting the future, like the video and hit subscribe for more stories where challenges, solutions, and results meet. In the comments, tell us if you think artificial intelligence should be trusted to predict the future, or is there a limit to what machines should know? Thanks for watching. Stay blessed and stay curious.